So there should be, all right, I will need to pull up a new one. I prefer, this doesn't matter, but there we go. Okay, so we are hopefully going to cover, I think we needed to finish up 1.3, maybe like one or two things. But then after that, we are going to do this. Okay. Ooh, what's this? Oh, crap. Okay, sorry. 1 second. I need to do this properly. Okay. Right. We're going to finish up 1.3. I think we just needed to talk about vector equations a little bit. And then we'll be able to move on to 1.4 and hopefully get to a little bit of 1.5. That's my plan. So we'll see how it goes. So we need to first look at vector system, or vector, the vector form of a system of equations. Right. So if you have a system, so I'll just go ahead and write one down. Looks something like this. X minus x2 equals 5. Oh, it should be x1. And let's say to this. Something like this, right? This is a system of equations, and we know we can write it as an augmented matrix. We've been doing that. But what we can also do is write this using vectors. So how we would do that is basically we would use our, so for each variable, there's a corresponding vector. And we just take this sort of column, right, that would make up one column of our augmented matrix. And instead we write it as a vector. So it would be 2, 1, minus 1. And then we multiply that by x1, right? That's that variable corresponding to that column. And then x2 will be multiplied by the column 1, minus 1, 2. So a column vector there. And then x3, we would have 7, 0, 1, or sorry, negative 7. And then this is equal to that last column we turn into the vector 3, 5, 0, like that. Okay. So here we have, this is basically writing this as a linear combination on the left-hand side, right here, where our weights are just the variables, right? Okay, so we could label these vectors. I'll just write the labels underneath. So A1, A2, and A3. And then the equation would become x1 times A1, x2 times A2, and x3 times A3 equals B. Right, so this one will be B. And then this is going to be the same. So this is just a different way of writing down our system of equations, right? So it's just the same thing written differently, right? And we can also use this notation. So say we wrote it as a linear combination in this way. We could also then write this as an augmented matrix. Sometimes this notation is convenient. So what we mean when we write A1, A2, A3, B like this This is really just the matrix formed by just taking those vectors and sticking them in as columns into a matrix, right? So this is going to be just the augmented matrix, right? So 2, 1, minus 1, 1, minus 2, 2, negative 7, 0, 1, and 3, 5, 0. So it's not, when we write this, just to be clear, it's not like a matrix containing vectors. You're really seeing it as just a matrix, and you form it using those as the columns. Does that make sense? Hopefully. Okay. So this is just, like I said, a different way of representing a linear system of equations, and sometimes having these different viewpoints is useful, you know, for solving problems. Okay, so you can check. So we talked about the span last time, I believe. There's a way that we can use this type of idea to check if a vector is in the span of a collection of vectors. So we can check if a vector B is in the span of two vectors u and v, or more, but we'll start with just two, by considering the system with this augmented matrix, right? So we just take U and V, and B is our augmented column, right? So how do we use this? Well, we know how to solve these, figure out if the augmented matrix represents a system that is consistent or inconsistent, right? And then once we figure that out, if the system is consistent, then we know that B is in the span of U and V. And otherwise, so if the system is inconsistent, B is not in the span. So I accidentally used this notation. So let me just say something about this. Let's see, I'll write this in a different color. This little symbol right here, this like E looking thing, this means we read this as in, but really it means that B is an element of this set, the span of U and V. Remember, the span of U and V is just a collection of vectors, right? So we could see it as a set, right? And a set is just something that holds a collection, right? So I'll probably continue using this notation just out of habit. I try not to, but a lot of the times I forget it. So if you see that, just read it as in. So this means B is in the span of U and V. Okay. Can this go away? Okay. So why would this be the case? So why is it that if this system is consistent, you do have a solution, or sorry, you do have that B is in the span? So let's think about why. Well, if this system, oops, U, V, and B is consistent, that means that we have at least one solution, right? So it has a solution, meaning that we can find x1 and x2 such that x1 times u plus x2 times v is equal to b. That's what it means for that to be a solution, right? And then looking at what this is, this is B written as a linear combination of U and V, right? So any solution of this system exactly gives us B written as a linear combination of U and V. So that's why it's the same thing to say that the system is consistent and B is in the span of U and V. Okay. All right. Oh, and then if we want to think about it the other way, if the system is inconsistent, then we cannot find x1 and x2 such that x1 times u plus x2 times v equals b. So that means that b is not in the span. Oops. And then we can do the same thing, like I said, for more than two vectors. So in general, if you want to know if B is in the span of a collection of vectors, say V1 up to Vk, then you just solve the system given by this augmented matrix. So you just take all of the vectors that are forming the span, you augment with the vector that you want to know whether it's in the span or not, and then if you get a consistent system, it is in the span. Inconsistent means it's not in the span. So consistent means B is in the span, and inconsistent means B is not in the span.
I have a question.
Yeah.
In general, do you want to find the weights x1 to xk, or is it enough just to say that V1 is or isn't in the span?
It's enough to say that, unless you're asked to specifically write B as a linear combination of those, in which case solving the system will help you do that as well, because any solution that you find would be a way to write B as a linear combination of those. Okay, so let's do an example, right? So the question is this vector B 8, 16, 3 in the span of U and V, where we have U is 1, 2, 6, and V is -1, -2, -1. Okay. So, like we said, we want to first write this as an augmented matrix. So we form that by taking U, V, and B, right? So we just stick these together in a matrix. And then we solve, right? So we just do our row operations and we try to solve this. I'm going to move this over just a little bit so I can have some room. Okay, so our first step, we can take row 2 and so it'd be nice to have it have a leading 1, right? So we'll just divide by 2. Oops. So we would get 1 minus 1, 8. Right? And then it's clear that you have your first row and your second row are exactly the same, right? So if you take row 2 plus row 1, that will, or sorry, minus row 1. That will eliminate that second row. So we'll get zeros there. And then in row echelon form, we want all rows of zeros to be at the bottom. So we'll go ahead and switch row 2 and row 3. So we have 6 minus 1, 3. Zeros at the bottom. And then we want to take care of row 2, right? So we can take row 2 and replace it with row 2 minus 6 times row 1. Right? So those two rows stay the same, and then what we'll get here is 0 for the first entry, and then we'll have, wait, yep, so that would be 6, yeah, 6 minus 1, so 5, and then we would get 3 minus 48, so negative 45. And if we want to scale this, we can just take row 2 and divide by 5, right? So 0, 1, negative 9. Okay. So that is our row echelon form, right? It's not quite reduced because we have this -1 above our pivot, but we can tell that we have a consistent system already, right? So this is consistent because we have a row of all zeros at the bottom, and then the others are, these correspond to pivots, right? So those will give us a consistent system, and we can actually figure out what that solution is going to be, right? So let's go ahead and do that, and then we can write our B as a linear combination of the two vectors u and v, right? Okay, so let's go ahead and do that. Let me clean this up just a little. Oh, uh-oh. So, okay. Writing down what this means, we get, I'll actually just use this area here. So, right. We get x1 minus x2 equals 8, and x2 equals negative 9. So we have our one piece of our solution, and then we just use that to figure out what x1 is. So x1 minus negative 9 equals 8. So we get x1 equals negative 1. Okay, so our solution is -1 minus 9. And if we want to write B as a linear combination, it would just be, we would just use these two, this solution, those two numbers to write. This one corresponds with U, so it'll be negative U minus 9V, right? Okay. So definitely B is in, this is in the span. I should write that. Is in the span of U and V. But we could also tell, oh, yeah.
Oh, never mind. You're going to answer it.
Okay, yeah. So we could also tell that back here when we saw that this was consistent. Right?
So if we just wanted to say that V was in the span, we didn't have to find the solution.
Yeah.
Cool.
Yeah. Okay. Okay. So I'm going to skip that. We're going to move on to 1.4. So here we talk about the matrix equation. And this is going to be an equation that looks like A times X equals B, right? Where remember that capital A we use for matrices. So first, let's talk about how to multiply a matrix by a vector. So multiplying a matrix A by a vector V. Okay, so just do this quickly. So let's just do this by looking at an example, right? So if I have my matrix, let's say it's just 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And I'll take a vector V, which will be 2, 1, minus 1. Okay, now I can multiply these two things together and we'll show what that will be. Now, to actually multiply a matrix by a vector, you need, so it's important to have that the number of columns of A should match the number of columns of A needs to match the number of entries or rows of V. Okay, and you'll see why when we actually do the computation, because if we didn't have that, it wouldn't work, right? So let's look at A times B, and we will have, so just writing out what these are, we have A and V, right? And the idea is to start with the first row. Okay, so I'm going to highlight it because we're focusing on that first row. And we're going to multiply it by this column vector, right? By taking the first entry of the first row and multiplying it by the first entry of that vector. Maybe I should do that in a different color. So take 1 times 2, right? And then we add, so we add 2 times 1, so the next piece. So this 2 times this 1, right? So we're moving along the row and at the same time moving along the vector, right? So we get 2 times 1, and then the last piece is 3 times negative 1, right? So, and we add that as well. Okay, so that's the first part. And we're actually going to form a vector. So the first row, we multiply by the first column, or not the first column, we multiply by the column vector, and then we move on to the next row. So now we're focusing on, I'll do this in a different color, this row, 4, 5, and 6. we do the same thing where we multiply the first entry by the first entry of the vector. So here we'll get 4 times 2, and then we add, moving along, we get 5 and 1, so 5 times 1, and then 6 times -1, right? And then in the last row, so now we're doing this one, we get, oops, 7 times 2 plus 8 times 1 plus 9 times -1, right? And then we just simplify all of this. So actually adding these things together, we get 4 minus 3. So the first entry is 1. We get then 8 plus 5 minus 6. So it's 8 minus 1. So 7. And then in the last one, we get 14, also minus 1, so 13. Okay. So this is just a something that if you haven't seen before, you should just practice a little bit to get the hang of. One thing to note is that when we multiply a matrix by a vector, it will have, or let me say this for the general case. So if we have a m by n matrix, right? And then we multiply it by a vector. Okay, so if A is an m by n matrix, where does V need to be? Like, what kind of vector is this? What length?
N times 1? No, that's not right.
Right, so it has to, like we said, the number of columns has to match the number of entries, right? So the number of columns of an m by n matrix is n, so it is in Rn, right? So V is a vector in Rn, right? So meaning we can do this multiplication, and what you get out of doing this multiplication is a vector in Rn, right? So just to visualize this, if we have A times V and we look at, so not actually writing down what the entries are, but we have some matrix that looks like this. It has some entries in it, like that. And we multiply it by, so it will have m rows and n columns. We multiply this by our vector from Rn, so v1 up to vn, those are the entries. This will be so what comes out of this is a vector in Rm, where m is the number of rows of the matrix, right? Okay, so like I said, just do some practice with this and you'll get the hang of it. A couple of properties that matrices have. Oh, okay. Or sorry, not matrices. That two properties, so there's two properties of this matrix times vector multiplication. So if A is an m by n matrix, and you have two vectors, u and v, in Rn, and C is a scalar, then we have these two properties. So first of all, A times u plus v is equal to A times u, oops, plus A times v. So it distributes in this way. And also, if you're looking at a matrix times a scalar times a vector, you can write it as the scalar times the matrix times the vector, like that. Okay. Now, one thing to note is that when we write C times A, we know how to multiply a vector by a scalar. To multiply a matrix by a scalar, this means multiply all of the entries of A by C. So, for example, if you have 2 times A, where A is the matrix 1, 2, 3, 4, you just multiply all of the entries by 2. So you get 2, 4, 6, and 8, like that, right? Okay.
Can you go a little bit up?
Oh, yeah, sure.
Thank you so much.
Yeah, no problem. Okay, so now we can talk about, okay, so just as a reminder, this class ends at 1:50, right? Okay, cool. Need to like keep that in my head. Okay. Okay, so now we can actually talk about the matrix form of a system of equations. So we started off talking about the vector form, and this is just another form we can write down a system of equations in. So matrix form. Right? And it looks just like what we wrote down in the title. So A times X equals B, where A is going to be your matrix of coefficients. So oops, of the system, right? And what we've done here when we write X is we've just taken all of the variables and stuck them into a vector. So this X will be X1, X2, up to Xn, however many variables we have in our system, right? Okay, so that means that N here is the number of variables. Okay. Okay. So this is what we will call a matrix equation, if we want to refer to that. Okay. And then this relates to the vector form of the equation. If we write A in this way, where we just form vectors out of the columns, right? Like this. So this is just the same matrix, right? We're just writing it a different way. Then AX is equal to X1 times A1, X2 times A2 to Xn times AN, right? So if we want to go from matrix form to vector form, we just split it up into the columns and write it this way, right? Okay. So now we have 4 different ways of expressing a linear system. So let's just make note of all of them right now. So first of all, we can write it as a system of equations just regularly. So this is what we started off looking at. Things like Let's see, 2x1 plus 3x2 minus 2x3 equals 7. And then another equation, say x1 minus x2 minus 3x3 equals 5. Sorry about the handwriting. I should really fix this. Okay, those are 3's. And then, so we just consider these together. These form a system of equations, linear system of equations, right? Secondly, the second thing that we learned about was augmented matrices. So we could form those by taking the coefficients. So augmented matrix. So in this case, we would get the following matrix like that. Okay, we just take the coefficients and we add the constants that at the end, right? And then we just learned about, let me put this on the next page.
Sorry, Professor Jones, these are the 4 different ways of expressing them, or how?
Right, expressing, so what I mean by that is that we have a system of equations and there's several different ways we can write it down, right?
Okay.
And then when we do this, we sort of work with it a little bit differently, right?
Okay, thank you.
Okay, so the vector form, this is where we write x1 times each of the columns, right? So we take the first variable times the first column, x2 times the second column, x3 times the third column, and then this last, that's b, what we usually refer to as b, right? Okay.
Dr. Jones, if you're given like one of these, can you convert it into any of the others?
Yeah, exactly. So it's convenient to be able to go back and forth between them, right? Yeah, so that's a good point. And then lastly, we have the matrix equation. I guess I want to call this a vector. It's a vector equation, right? And then this is a matrix equation where we just take all of these columns. So this is similar to the augmented matrix, but we'll write it in this way. So we have our matrix times x, which is our vector of variables, right? And then we set that equal to 7, 5, right? Okay. So this is in the form ax equals b.
Could you write out the x vector as x1, x2, x3?
Yeah, you could. Yeah. So
Thank you.
So right.
Can you go back to where you first mentioned the matrix form of a system?
Yeah.
Okay, yeah.
Mhm. Okay.
So I'm assuming there are benefits to each method of writing them. So in the sense where you would approach the problem, I guess, knowing, okay, I should probably write down the these expressions in this form of a matrix, right?
Right. And usually the most convenient way is to write it as an augmented matrix, right? It's sort of the most compact. So this is how we usually work with it, because we can do those row operations and it's really convenient to do it that way. What we can do from there is, so a lot of the time when we're solving, or I guess all the time when we're solving, we go from the augmented matrix, we reduce it, and then we write it back as a system of equations, right, to get our solution out. And so that's an example of like moving back and forth between them, right? And then we'll have these other ways of looking at it, which will be useful as well.
So
Cool, thanks.
would you say that the vector equation and matrix equation are better for like seeing the characteristics of the equation and not actually solving for it? So like if you wanted to extrapolate out like data, like looking at how they get graphed, they might be easier to like graph or like see certain things that might not be apparent in the other forms.
Right. Yeah. So like for instance, the vector equation, this is on the left-hand side, that's a linear combination of those vectors, right? So that can be a nice way to see that when we're thinking in terms of like the span of those vectors or that kind of thing, right? So that's why it's like a different mindset of looking at this same like system of equations. Hopefully that made sense. Okay, so we'll be working with all of these, right? So these will come up again. Now we have something that we can say about how these relate. So we have some equivalent statements. And what equivalent means is that, so we're not just here, but all the time. When we say equivalent in math, this means all the statements, so two options, either all the statements are true or all are false. Right? So if we know one, so for example, if we know that one statement is true, they are all true. Okay. So this is useful to be able to write down things that are equivalent, right? Okay, so given a matrix, so suppose we have a matrix A, which is an m by n matrix, and we know that its columns, so we'll just label them. We have columns A1 up to AN, and we also have a vector B, which will be in Rn, yeah. Okay, then the following are equivalent. Okay, so first of all, our first statement is that B is in the span of these vectors. A1, okay, stop, up to AN, right? That is equivalent to saying that X1, A1, we do 2, plus X2, A2, plus Xn times AN equals B. This vector equation has a solution. And then that is also equivalent to saying that the matrix equation AX equals B has a solution. Okay. Okay. So we kind of talked about this earlier when we talked about how to figure out if a vector B is in the span of a collection of vectors. So this is just taking our different ways of writing that and putting them into this format and saying that they're all equivalent, right? Okay. So let's see. Like I said, so we talked about how to figure out if B is in a span of a collection of vectors, but there's another question that we might ask. So just to put that all down. So we know how to figure out if B is in the span of just a collection of vectors. We can also ask a different question. So whether any B, any vector B is in the span of use A1 up to AN. So emphasis being on any, right? So if I took any vector B, can I write it as a linear combination of A1 up to AN? Is this like part? Possibly. I'm not quite sure. Do you have the like statement of that problem?
Yeah, I think it was, are there any vectors that do not exist in span U comma V?
Right, yeah, so that's a related question. Yeah, exactly. It's sort of like the inverse of that. Like, can you
Cool.
any that are not in there? Yeah.
I was wondering, because I feel like kind of the cheating answer would be like, if it's in an Rn greater than the vectors in the span, then like it automatically wouldn't be in the span.
Yeah, it would automatically.
But that felt like cheating.
Yeah, so this B should match the space that those vectors are in, right? So yeah. Okay. So last one place. So what this means is that if we have vectors, so if A1, wait, let me try and write this a little bit neater. Okay, if A1 up to AN are vectors from Rm, then if this is the case, is that how I want to state this? Okay, I have to make sense of this. So what I'm trying to say is that if this is true and A1 up to AN are vectors from Rn and B is also a vector in Rm, that means that any vector B can be written as a linear combination of A1 up to AN. And then that also means that these vectors A1 up to AN span all of Rm, right? Okay, so we're gonna like put this all down in a theorem. So we're gonna write out, maybe I should write it.
Question, Professor Jones?
Yeah.
What do you mean if true? Like, what is true in this case?
So if it's true that B is, if it's true that any B is in the span of these.
Oh, thank you.
So I guess this,
A little confused as to what it means specifically here that A1 all to the AN are vectors from RM. Like,
I am, oh, I'm just like making it explicit that, so I should have written this here, any vector B from Rm can be written as a linear combination, and also that the span of A1 up to AN is in fact equal to Rm.
okay, cool.
Does-
Thank you.
Okay, cool. So I didn't write that down because I was going to write it down in the theorem, but it doesn't hurt to write it twice, so it's fine. I'm going to write this down here so we don't, so it's not split into 2 pages. Let's see. So here we have our first theorem. This says that if we have a matrix A, which is an m by n matrix, with columns A1 up to AN, right? And a vector B in Rm. We have some more equivalent statements, right? So the following are equivalent. So first of all, so this is going to be similar to some of the equivalent statements that we talked about earlier. So every B in Rm is in the span of the columns A1 to AN, right? And another way of saying this is that the columns of A span Rm, right? Okay, so that's our first statement. This is equivalent to saying that every B in Rm can be written as a linear combination of the columns. So A1 up to AN. And then this is also equivalent to saying that the matrix equation AX equals B has a solution, or has a solution for every B, right? And finally, we have one more. It's that the matrix A has a pivot position in every row, right? Okay, so the emphasis in this statement is that the emphasis in each of these statements is every, right? It occurs in every one of these statements. So every B is in the span. Every B in Rm can be written as a linear combination. This matrix equation has a solution for every B, and A has a pivot position in every row, right? So just to emphasize that. Now let's do an example where we are using this fact, this theorem. So, right. So we might ask, do the columns of a matrix A, which we'll write down in a second, span R3? That's the question. Here's the matrix. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so here's our matrix. We want to go ahead and figure out whether this will span R3. So we're going to use the, well, basically we're going to row reduce this and look at the pivots, because that will be the easiest way to go about this. So again, we're just row reducing, right? So I'll start with replacing R2 with R2 minus 5 times R1, right? And then I will get 1, 2, 3, 4, 0, negative 4. We'll get negative 8 and 8 minus 16. So, wait, did I do this right? Oh, 8 minus 20. Okay, negative 12. And then leave the other one alone. Great. And then we can replace row 3 with row 3 minus 9 times row 1. Okay. Here we get 1, 2, 3, 4. 0 minus 4 minus 8 minus 12. And then in the last row, we'll get 0, negative 8, negative 16, and then 12 minus 36, so negative 24. And that should be correct, yeah. Okay, so here we are, and you might notice that the last row is a constant multiple of the second row, right? So we can actually get rid of the last row by taking, let's see, row 3 and replacing it with, we need minus 2 times row 2.
Could you stop there? Because if there's a constant multiple, you know, one row is going to be all zeros, which means no pivot point, which means.
Exactly. Yeah, so we can, once we get here, we'll get all zeros.
Or
So
do you want to see the last step?
I would like to see the last step.
Okay.
Yeah, the conclusion. Yeah. So you can see here that A does not, so A does not have a pivot. In every row. So that means that the columns of A do not span R3. Okay.
Can you go back to the statement of the theorem?
Mhm.
Okay, yeah. Okay, just want to copy that down.
Okay, yeah.
So I have a question. So like, is there any sort of connection between every B, blah, 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 being in the span, and like an augmented matrix having infinitely many solutions.
Right. So if the augmented matrix has infinitely many solutions when you form it using A and B, right? Then you cannot write every B as a linear combination, meaning that it's not every B is in the span of the columns. Right. Right.
Okay, that's a little confusing, but I'll try to just let it sit.
Yeah, exactly. Just let it. Right. So a lot of there's going to be a lot of equivalent statements in this class, and sort of being able to like move from one viewpoint to another is going to be really helpful, but also a little bit confusing. So just try to like think through it in your mind. Looking at examples is really helpful. And yeah.
Oh,
Yeah.
sorry.
Yeah, go
It
ahead.
just seems contradictory to me. Like, I feel like if a specific B has infinitely many solutions, then I don't know, it doesn't make like logical sense.
So
I can't connect it.
right. So for instance, here, like we did this example, right? And this is, it is not, what am I trying to say? Okay, so A, let's rewrite it. It row reduces to just taking the last step and then dividing the second row by -4. So we would get something, yeah, 0, 0, 0, 0. Right? In this example, we already said it doesn't have a pivot in every row, so it does not span R3, right?
So in that, does that mean like every vector B cannot be written as a linear combination of these vectors?
Exactly.
Okay.
So yeah, we could actually, I'm going to do an example of that in the next thing. But yeah, not every vector can be written this way. And we can actually figure out which vectors could be written this way. But instead of using this example, since it'll get a little convoluted, I'm going to do it in the next example with a smaller matrix. So.
Okay, so the A matrix here represents the coefficient matrix.
Right. A is the matrix of coefficients. Yeah.
Okay, cool. Thank you.
Yeah. So just to like write this out. So this means that this equation does not have a solution for every B, right? But it does have a solution for some, right? And you can just think about what would happen if you create an augmenting matrix using this. I'll just use the row reduced form, right? So 1, 2, 3, 4, 0, 1, 2, 3, 0, 0, 0, 0, right? If we had a B that did not have 0 in the last entry, so say we had a 1 here, so if B equals, let's say 0, 0, 0, 1, right? We get an inconsistent system, right? That's showing that it doesn't work for every B, but if B equals 1, 1, 0, then this is consistent. It's just not always consistent for every B.
Are there any are there any instances where AX equals B does not have a solution for any B?
Is
You have different dimensional vectors.
well, okay, let's see. Can we can have an inconsistent system, yes. So yeah, that is possible. Wait,
Is it important to be able to recognize that? Like when it's every B, when it's some B, and when it's none?
sorry, I'm still thinking through that. Hold on.
Oh, I think I'm inventing the like whole trivial solution and non-trivial solution thing. I
Yeah.
just invented, okay, I'll let you talk.
Okay, so there
Sorry.
is it's not possible to have none. It's possible to have only one solution. So if you think about it in terms of I don't know, I'll just put some stars here. So if I have a matrix, right? A solution to this means that B is in the span of the columns, right? Now, the only way you're going to get nothing, or you can't get nothing in the span, you can have that the span of the columns is the smallest thing you can get is just the zero vector. So possible. Okay. So the smallest thing you get is just zero. That's the trivial solution, right? That would only happen if all of your columns are the zero vector. If you have at least one non-zero column, then your span has to be at least one dimensional. Remember we talked about it being like a line or a plane or 3D. It has to be one of those. And so it has to have something in it, right? So you'll have some solution. So yeah, you actually will always have something in the span of the columns, even if it's just zero. Okay. Now let's do one more example. Okay, so we might ask, instead of whether all of the vectors in a space are in the span, we might ask which vectors are in the span, right? So what vectors B are in the span? So I'll write it this way. Are in the span of these two. So we'll have 3, -9, and -1, 3. Okay, and how we can do this is to consider an arbitrary vector B. So we'll just write it as B1, B2, and then we'll just set up our augmented matrix using that. Okay, so our augmented matrix would be, we stick the columns together. So those vectors there, and then have B1 and B2 in our augmented column, and then we row reduce, right? So here we can take row 2 and replace it with row 2 plus 3 times row 1, right? And we will get, we will get this in the first row, and then in the second row we will get, in fact, 0, 0, and b2 plus 3 times b1. Is that legible almost? Okay. So, and now we're done. We're reducing, right? We just needed one step. This is consistent if what?
If
If
b2 plus 3b1 is
equals
0.
Yeah, exactly. So if b2 plus 3b1 equals 0. So this is a constraint, right? So it tells us what has to be true about that vector b in order for it to be in the span. Okay? So just solving for b1 in terms of b2, we can rewrite this as, so this means that b1 should be negative 1/3 of b2, right? So this means that if b is in the span of our vectors, then it should be of the form it should be negative 1/3 t and t. So what I've done is just replace b2 with t, right?
That then becomes a factor.
This here, then I'll write this out in words. Then b is of the form like this, where t is a real number. Okay. So we are out of time. So we almost made it to 1.5. Not quite. But I guess we'll be doing that next time. We did already talk about this sort of like parametric way of writing solutions. We're gonna delve a little bit deeper into that. And then also talk about the homogeneous system of equations and trivial and non-trivial solutions. Okay. So
I have one quick question.
yeah.
So about if you go back to the theorem,
Mhm.
the equivalent statements.
Yeah, this one.
Yeah.
Mhm.
So I get the first three, but I don't really get how the matrix A has to have like a pivot position
In every row. So it is, so remember that the issue came here when we had this row of all zeros at the bottom, and that
Right.
meant we could create inconsistent systems by just like having a non-zero entry corresponding to that row of all zeros.
Okay.
Right? So if you don't have a pivot position in every row, it leaves open that possibility of creating an inconsistent system. Does that make sense?
Okay.
But you can have columns that aren't pivot columns.
Yeah, you can.
So there doesn't need to be a pivot position in every column. There just needs to be a pivot position in every row.
Yeah, exactly. Yeah.
Okay, cool. Nice.
Yeah, no problem. Okay. So did that answer your question?
A little bit.
A little bit. Yeah, just again, just mull it over. It'll so like these ideas need time to like set in, I think.
Yeah.
Yeah. Okay. So yeah, like I said, we'll do 1.5 next time and hopefully get to 1.6 as well. So do look over that section as well. And then I will see you guys next time. And also, if you have any issues with the homework, just send me an email and I'll try to help you out.
Thank you, Professor Jones.
Thank you.
Professor.
Thank you.
A great
Sorry
day.
for
Thanks a lot. See you
having
next time.
questions.